I've got another simulation here to show us the zeroth law of thermodynamics. This simulation is, I think it's really neat. It's really simplistic, but a lot of the things that I like are. But what it allows us to do is we can first off click this little checkbox showing us how much energy is in each of these objects. Then we'll be able to heat them up, cool them down, put them together. I'm also going to put the water on top of the first heater so I can add energy to it or I can take energy away from it. See that? I can grab this little guy, I can put a thermometer on that so I can see relatively how much heat is there. What I'm going to do is I'm going to grab this little iron block, I'm going to put it on top of this. I'm going to give this one a thermometer as well. So I'm going to put the temperature of the water all the way down, as low as it can possibly go. And then I'm going to heat up the iron. I'm going to add as much energy to that as I possibly can. And so what I'm going to be doing is creating an energy difference between these two substances. So one is going to be hotter than the other. That's just a really fancy way to say one is hotter. Once I get it up to temperature, then I can take the iron and I can drop it into the water and I can watch how the temperatures move. Notice at first they move really fast, but as they get closer and closer to even, they start to slow down until finally they get to a perfectly even temperature, and then they stop. The energy stops changing. So now these two systems are at thermal equilibrium with each other. So I can take the iron out, take it out, there we go. I can add a thermometer to the brick, and I can do the same thing with the brick. I can take all of the energy that I can possibly take out of the water, and then I could add the temperature into the brick, and I could put that in. And what that would show me, we could do this in the lab as well, what that would show me is how much energy does the brick contain versus how much energy does the iron contain. Do they contain different amounts? And I can do the same thing with the oil. Does the oil increase its temperature more or less? So it takes a certain amount of energy to change these temperatures. So where they're going to even out really depends on the substance. So if I drop the brick in here, we could track that and we could try and see how similar are those two temperatures. You take that back out, switch it out, try the oil. Boop, 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 boop. Put a thermometer on that one. Right here. Drop its temperature all the way down. We're going to do the same thing one last time. Adding temperature to the brick, adding energy. It's increasing in heat. Doop. And we get there, maximum temperature, and now I'm going to drop into the oil. We're going to see. The oil reaches a higher temperature than the water did. It takes less energy to heat up the oil than to heat up the water. So, these are now in thermal equilibrium with each other, so there's not going to be any change. So that's the zeroth law of thermodynamics in action. But why is it called the zeroth law? Well, the reason it's called the zeroth law is because it was actually found after the first three laws, after 1, 2, and 3. We were able to define this really fundamental idea, but we defined it so much later, we went, well, you know, we really shouldn't call it the fourth law of thermodynamics because it's a simpler idea. It should come before number 1. Well, what comes before 1? Well, 0 does. So instead of trying to redefine the first, second, and third laws, we went, just make it 0.